Hi everyone, today let's talk about oxygen minimum zone. OMZ are area in the ocean usually between 200 and 1000 meter deep where oxygen levels are so low that most marine life cannot survive. OMZ are common in upwelling regions like the eastern tropical Pacific and the Arabian Sea. Despite being low in oxygen, they play a huge role in the ocean carbon and nitrogen cycle, especially through processes like denitrification. But here, the concern is OMZs are expanding due to climate change, threatening marine ecosystem and fisheries.
Water column of oxygen minimum zone contain upper oxycline, core of the OMZ, and lower oxycline. In the upper oxycline, just beneath the euphotic zone, it contains some oxygen which influenced by the surface productivity. Organic nitrogen from the sinking dead plankton and waste begin to accumulate here and to prepare to support the microbial activity below. One major process occur here is nitrification. Next is the core of the OMZ. It occurs in mesopelagic zone. The oxygen level here is extremely low and sometimes is absent. Due to the absence of the oxygen, microbes rely on anaerobic respiration. Two key processes dominate here is nitrification and NMOX. Lastly, below the OMZ is lower oxycline. The oxygen begin to slowly increase due to the thermohaline circulation and deep water mixing. The key process in the lower oxycline is remineralization, where the organic nitrogen break down into ammonium and phosphate. In the onshore region, the sulfate reduction. The figure shows the water column of the OMZ. It is also important to distinguish between the offshore and onshore of OMZ zone. The offshore region is the farther from the coast that have more stable water column and fewer sediment interaction. Meanwhile, onshore zone is closer to the continental and have more complex biogeochemical activity.
Nitrification, oxidation of ammonia NH3 to nitrate and O3 minus by nitrifying bacteria, which is Nitrosomonas and Nitrobacteria. It converts nitrogen into a form usable by phytoplankton. Two steps involved in the process: ammonia oxidation and nitrate oxidation. So the nitrification in OMZs. Occurrence in OMZs despite low oxygen levels. Nitrification still occurs in OMZs, especially at the upper boundaries where oxygen is present in trace amounts. So the impact of the marine ecosystem. This process reduces fixed nitrogen in the ocean and influence greenhouse gas emission such as nitrous oxide, N2O minus.
Assalamualaikum. Hi guys. So, denitrification is a natural process that happens when there's low oxygen in the water, usually at the bottom of the ocean or lakes. In the process, bacteria converts nitrate into nitrogen gas, which is then released into the atmosphere. It's important because it helps reduce excess nitrate, preventing things like algal blooms that can harm the ecosystem. But there are also downsides if it's not balanced. For example, it can remove essential nutrients that aquatic plants need, and sometimes it produces greenhouse gases like nitrous oxide, N2O, which is contribute to global warming. So, in short, nitrification helps stabilize nitrogen level in water, but we also need to be aware its side effects. So that's all.
NMOX is an anaerobic ammonium oxidation process by converting ammonium and nitrite into nitrogen gas by NMOX bacteria. Nitrite is produced in the oxygen minimum zone by other bacteria through the oxidation of ammonium or the partial reduction of nitrate. Ammonium is released from the decomposition of organic matter and from excretion by marine organisms. These bacteria absorb both ammonia and nitrous oxide by converting them into nitrogen gas. NMOX is a major pathway for nitrogen loss in the ocean, especially in OMZ, where it can account for up to 50% or more of total nitrogen gas production. By removing fixed nitrogen from marine ecosystem, NMOX help regulate global nitrogen levels and influence productivity and carbon cycling in the oceans.
Next, I'll be explaining the phosphorus cycle. There are a few key steps in the marine phosphorus cycle. Phosphorus cycle begins with weatherings of rocks. Phosphate-rich rocks on land are broken down through chemical and physical weathering that release phosphate ions. Next, phosphate ions are carried into marine environments through rivers, surface runoff, and groundwater flow. Once in the ocean, phosphate is taken up by phytoplankton that absorb dissolved phosphate for growth and reproduction. Zooplankton and small fish feed on phytoplankton, transferring phosphorus up the food chain to the larger marine animals. When these organisms die, they remain sink in deeper water where the decomposition of organic matter takes place. Next is mineralization. Microbes convert the remaining organic phosphorus into inorganic phosphates. Some of these phosphates become bound to particles and undergo sedimentations. Not all phosphate sinks. In the water column, phosphate is actively recycled by microbes like bacteria and protists. In upwelling zones, phosphate-rich water are brought back to the surface by ocean currents. Lastly, in oxygen minimum zones, microbial activity becomes even more intense.
Here we've looked on the oceanographic sulfur cycle, especially in ocean minimum zone or OMZ. In this lower oxygen area, bacteria reduce abundant seawater sulfate into hydrogen sulfide using the organic matter. This sulfide is then oxidized by microbe using the nitrate or oxygen, forming intermediate compound like elemental sulfur, tiosulfate, and sulfide. This compound cycle between form being oxidized back to sulfate or reduced again to sulfide. The organic sulfur compound also feed into the cycle through microbial breakdown. And thirdly, the sulfur cycle is tightly linked with the nitrogen and carbon cycle and can be influence greenhouse gas emission. This play a major role in regions like Eastern Tropical Pacific and Arabian Sea. And in short, sulfur cycling help regulate marine chemistry and impact climate change, based on article by Kohlberg et al. 2021.
For the effect of OMZ, first, alteration to the nitrogen cycle. In the water column, OMZ increased detrinification and NMOX, which result in the loss of bioavailable nitrogen. This has an impact on production and nutritional balance. Second is pressure on marine life habitat. OMZ forced many aerobic creatures such as fish and zooplankton into restricted oxygenated layer, limiting their vertical habitat range and increasing competition and predator-prey interaction. Next is variation in macrobiological communities. Anaerobic microorganisms such as those engaged in the metabolism of sulfur and methane are favored by low oxygen level, which causes change in the composition of the microbial population in the water column. And lastly is accumulation of greenhouse gas. Nitrous oxide, NO2, a powerful greenhouse gas, is produced in large quantities in OMZ as a result of inadequate detrinification in low oxygen environment.